Okay, we're going to start so that Mr. Tokayer has the full amount of time with you. And he said, hello, everybody. He's hoping that there will be time for Q&A at the end. So let's begin right away. So I'm so glad that so many of you could come. It's a real testament to your intellectual curiosity and to Mr. Tokayer. Last year, Mr. Tokayer came and spoke to us about the discoveries of the James Webb Telescope that had been named by Science Magazine as the breakthrough of the year. And it was just that telescope was described as the largest, most advanced telescope ever launched by humans. And we were told that it would allow scientists to see views of galaxies and stars forming at the beginning of time, only a few million years after the Big Bang, which was 13.8 billion years ago. We're so fortunate that this year Mr. Tokayer agreed to come back to speak to us about another burgeoning field on astrophysics, exoplanets, as you can see in his title. Are we alone? The new search for other worlds and habitable planets beyond the solar system. What have scientists learned so far, and what do they hope to learn? I was just saying to Mr. Tokayer that yesterday there's a full page in the Science Times about the search for life on other planets. So I'm going to keep my introduction short so Mr. Tokayer has the full amount of time with you. Mr. Tokayer graduated from SAR High School in 2009, and he returned as a teacher in 2014. After leaving SAR in 2019, Yaron joined the Columbia Astrophysics Lab at Columbia University. During that time, he continued to teach high school STEM and also co-directed the Machon Siach Graduate Fellowship here at SAR. Yaron holds a bachelor's degree in engineering from Cooper Union and a master's degree in the philosophy of physics from Columbia University. He's currently pursuing his PhD in physics from Yale University, where he studies cosmology and high-energy astrophysics. Although we were so sad to see him leave SAR, we are thrilled that he's getting to pursue his dream and that he's come back to enlighten us on this major new area in astrophysics. I'm sure you'll all join me in welcoming Mr. Yaron Tokayer.
All right, hi, everyone. So cool that you came to spend your free period here to talk about planets and space. So on the one hand, the search for other worlds and the possibility of life beyond Earth is kind of the most fundamental and basic form of space exploration. And yet we've only really begun that search in earnest pretty recently, let's say in the past couple decades, 15 years. It's really a nascent area as far as our understanding of space goes. And my goal is to share some of that with you, what we know so far, and some of the open questions. And before we start, I just want to make sure we're all on the same page when we talk about galaxies, stars, planets. So I just want to do a little tour of the universe. We're starting all the way zoomed out. This is what we call the cosmic web. And if you look closely, you'll see that this structure is actually made out of these tiny little, well, they look tiny, but they're actually giant dots. And if you zoom in, you see that these are all what we call galaxies. Galaxies are collections of hundreds of billions of stars that are all bound together. We too live in a galaxy. It's called the Milky Way. And we're slowly zooming in, and I'm going to speed this up. So here you see on the right, this is actually the Andromeda Galaxy. And to the left is the Milky Way Galaxy. The Andromeda Galaxy is our closest kind of major galactic neighbor. And we actually think that in a few billion years, it'll collide with the Milky Way. And the Milky Way is over here. This is where we live. And if you zoom in, you'll see the hundreds of billions of stars that make up the Milky Way. These are all the stars in the night sky. Everything we see in the night sky is pretty much all stars in the Milky Way. If you keep on zooming in, we'll get to our stellar neighborhood, and eventually we'll zoom in on this star, which we call the sun, and all of these objects, really trillions of objects that are under the gravitational influence of the sun, is what we collectively call the solar system. Among those objects are planets. Here we're seeing the outer planets, Jupiter, Saturn, the asteroid belt, and we zoom in on the inner planets, Mars, Venus, Mercury, and of course, Earth, where we live. If we keep on zooming in, eventually, maybe we'll see us and, well, California. But anyway, so that is what we mean when we talk about planets. Those are objects that orbit stars. Stars together make up galaxies, and the universe itself has hundreds of billions of galaxies. So almost everything we see in the night sky, those are stars within our own Milky Way. And people have imagined the possibility of other worlds for the longest time. And think of all the books and movies that are based on that premise. Which raises the question, well, is that true? Do these other stars themselves have planets? We know that, obviously, the sun has planets. We're one of them. Do these other stars have planets? Now, based on this presentation, the answer is obviously yes. But we actually didn't know that for sure until 1992. And it could be interesting to think, what made us think so prior to that? I want to just start by showing you one of these just to prove to you that I'm not lying. This is the constellation Pegasus, where we live you can see during the fall and the winter. And there's one star, it's part of the constellation Pegasus. It's called HR 8799, one of the many catchy names that we have for stars. And it's 133 light years away. So that means it takes light 133 years to travel from that star to us. And if you would try to go in a spacecraft, it would take about 1 million years to get there. So it's really, really far away, but it's in our galaxy. And with a good telescope, you can see it. It's part of this constellation, or it's in that constellation. And if you zoom in really far with the Keck Observatory, which is in Hawaii, this is actually what you see. So you have a star in the center, and you might see these 4 objects that are all orbiting that star. Those are planets, what we call exoplanets, extrasolar planets. Those are planets beyond our solar system. And on the bottom, you can see the date. So these are pictures that were taken over the course of about 10 years, and you slowly see these planets orbiting the star. It's incredible. This is a direct image of a planet and proof that there indeed are planets beyond our solar system that orbit other stars. There are planets around other stars, and we think that there are many. Now, one of the things I wrote in the blurb for this talk was that we actually know much more about galaxies that are millions and billions of light years away than we do about planets that are in our own galaxy. Which is kind of wild if you think about it, because these are so much closer, which raises the question of why. Why is it so hard to find exoplanets? How do we find them, and why is it so difficult? Any ideas of why it's so hard to find these objects? Yeah. They don't create their own light, sort of, yes, exactly. And the light they do create, they say, is very dim. That's definitely true. Yeah. They're very small. Excellent. They're very small. They're very dim. And they're very far away. Wow, these are the exact bullet points I'm going to have on the next. You guys are really, really good. Any other ideas people have? Yeah, in the back. One more time. They move. Yeah, they move. So it's actually we'll see. You can actually use that to our advantage. That is very true. So why is it so hard? They're very small, like we said. They're very dim. They're very far away, and on top of that, they're very close to very large and bright objects, meaning the stars that they orbit. So, as by analogy, you can imagine you're trying to look at a bug, and that bug is next to stadium lights, and all of that is across the ocean, and you're trying to observe it. That's kind of what it's like to try to find an exoplanet. And just to really hammer the point home of how hard it is to see these planets, here's a picture of a planet. Does anybody know what planet this is right over here, that little dot? Okay, all good guesses. It is in our solar system, and this is actually Earth. This is a picture of Earth. It's taken in 1990 by the Voyager 1 spacecraft. This is what Earth looks like from the planet Saturn. Now, for all intents and purposes, Saturn and Earth are in the same place. And this is how puny and dim Earth looks just from Saturn. So you can imagine what it would be like to try to find a planet that's beyond our solar system. And we saw in the video at the beginning how far away that actually is. So given these challenges of how hard it is to detect exoplanets, how do we do it? What are some of the clever ways that we can try to find an exoplanet? Do you have any ideas? Yeah. So once we know there's a planet there, we actually can try to learn things about its atmosphere. That's true. But you have to know the planet's there to begin with. Yeah, on the side. Okay, so maybe you could send a spacecraft to some faraway star and see if there's a planet there. It's a great idea. The problem is that it would take a really long time to get there, which is what we were saying at the beginning. So even that star, which we saw, was 133 light years away. Our closest stellar neighbor is called Proxima Centauri. That's 4 light years away, which would take about 60,000 years to get there by spacecraft. So we could do it. We just have to wait a long time to get the results. Yeah. Yeah. That's such a good idea. Yeah, we call that time domain astronomy, and that is actually part of how we find planets. You kind of stare for a really long time, and you look for certain changes, and we're going to talk about some of those changes now. So the first method we use is actually what we call the transit method. You can imagine that bug that we talked about in front of the lights. If the bug passes in front of the light, you'd imagine that the light very, very slightly gets dimmer. And that's true for planets as well. You imagine a planet orbiting a star, and if you're facing the right direction, then as the planet passes in front of the star, you might see the star get a little dimmer. On the bottom left, you can see a graph of how much light you're detecting over time, and you see that it dips when the planet passes in front. Now, this is highly exaggerated. I'll show you some real data in a second, but this is actually the most successful method we have at finding exoplanets. You stare at stars for a really long time and look for their brightness to go down. So here's real data. This was published this month in April 2024. So this is a time series where you see the brightness of the star over time. And does anybody see the transit? This is just a gap in the data, so this doesn't count. But does anyone see little dips? There's one right over there. There's a transit. There's a transit right over here. And this one, which was taken at a much higher cadence, that's why there's more data points. There's a little transit over here. So those are the sorts of things that we look for. Now, this is an extremely subtle effect. Here on the y-axis, this is parts per million. So 1,000 parts per million, that's in 1,000th. So these things go down by about 0.1% in brightness. And when you clean up all this data, you get something that looks like this. So this is called the normalized flux. So one is like the regular brightness of a star. And you see it goes down. It's not even 0.99, which would be going down by 1%. And it took about 4 hours here, from -2 to 2 hours, as this planet passed in front of its star. Here's another set of data that was taken last month, or that was published last month. And again, you see this dip. And this is, I just want to show you what real data looks like. You know, we have all these artistic renderings of planets, but those are just artistic renderings. This is really what planets look like to us. They look like, you know, graphs in papers that we get from telescope data. But don't worry, we'll also have some fun pictures later on. So that's our first method that I want to talk about for detecting planets. Now, anytime you're doing any physics experiment, including trying to find exoplanets, you need to think about the kind of systematic errors. What are the biases in the data? What sorts of planets would this be really good at detecting? And what sorts of planets would this definitely miss? Because you want to make sure that you're interpreting the data correctly. So you could think about the transit method. What are its selection effects? What are the things that you think would make a planet a really good candidate for finding via the transit method? And what would make it a bad candidate? Yeah. If it's large, excellent. Why? Exactly. It'll block out more of the starlight. So this is going to preferentially find larger planets, and smaller planets won't be able to be found this way. In the back. Yes, excellent. You want planets that are really close to the star, and that's for 2 reasons. First of all, it's going to block out more of the sunlight. Second of all, it's going to orbit more frequently, so you're more likely to find it. Yeah, David? Depending, say more? Yeah, that's such a good point. Exactly. You need to be oriented the right way. So, and I'll have a picture of this. So, first of all, large planets, which somebody said, it blocks out more light. Second of all, you need to have what we call an edge-on view. What does that mean? Imagine you're looking at a star and you have a planet going around it, but you're oriented such that the planet never passes in front of the star. The transit method won't pick up this planet. If instead it's edge-on, then as the planet passes in front, then it'll block out the starlight. So this is only finding planets that orbit their stars that are oriented just so that it'll block out the light. Finally, planets that are near the host star, like was also said, those are going to orbit more frequently, and those are going to block out more starlight. So we won't talk about the selection effects for all of the methods we talk about, but just have that in mind anytime you learn about a new method for detecting planets or for detecting anything, any sort of physics experiment. You always need to think about what are its selection effects. Before we get on to the next method that we have for finding planets, I want to do a little physics lesson interlude. There are kind of two physics concepts we need to know about in order to fully appreciate this next method. The first is what we call Doppler shift. So you can imagine a star that's emitting light, emits light in all directions. Wonderful. And maybe that light has a color, maybe it's green, and you can have observers on all sides, and they'll all see green, and they'll agree, I see green, me too. Great. What if instead the star was moving? So if the star is moving while it's emitting light, so then as it emits light, it kind of gets scrunched up on one side, on the side that it's moving toward, and it gets stretched out on the other side. Why does that matter? That matters because it turns out that by stretching light or scrunching it up, it actually changes the color of the light. So if it's emitting green light and you scrunch it up, it's going to get bluer. We call that a blue shift. And if you stretch it out, it's going to get redder. Red light has a longer wavelength. It's more stretched out than it's the most stretched out part of the visible color spectrum. So now this star is emitting green, but somebody on either side are seeing different colors. Somebody for whom the star is moving away sees red. Somebody for whom the star is moving toward them sees blue. That's called the Doppler effect, which also applies to sound, by the way. You might hear on a highway if somebody's honking their horn on the other lane, then it goes, ah. That's also the Doppler effect. It's the sound getting scrunched up and then stretched out as it goes toward you and then away from you. So the same thing happens with light. We call that blue shift and red shift. Okay, why does that matter? It matters because of the second fact that I want to share with you, which is that planets don't just orbit their host star. That picture I had was actually very misleading, where it just showed a planet going around the star. Really, the two orbit each other. Not only does the star tug on the planet tugs on the star. So this picture is not totally accurate. A more accurate, although a little bit exaggerated picture is something like this, where both are kind of getting tugged by each other. They're orbiting about a common center. Okay? Why does that matter? Think about what we talked about in the last slide. If the star is getting tugged back and forth, that means sometimes it's moving toward us, sometimes it's moving away from us. The light will get blue shifted and red shifted periodically, and we can use that signal to find evidence of a planet that is orbiting that star. So here's just a little animation. You have a planet and star orbiting each other. They're both tugging on each other. And again, if you're facing in the right direction, then as the star moves away from you, you see the light gets redder, and as the star moves toward you, it gets bluer. So we call this the radial velocity method, because what you're detecting is the speed of the star as it goes away from you and toward you. By looking at how red it gets and how blue it gets, you can convert that into a speed. So as promised, I want to show you real data. Here's real data of the radial velocity method. You see that the velocity of the star goes up and down. It's getting tugged back and forth as we see it. This is a fun example because it's the star Proxima Centauri, which is our closest stellar neighbor that I mentioned before. It's 4 light years away, and there's indeed a planet that orbits Proxima Centauri. And the reason we know that is because of this radial velocity method. If you stare at it long enough, you see the light over the period of about 10 days get redder and bluer. Now, a period of 10 days, by the way, is very short. So the period of Earth, for example, is how long around the sun? 365 days. Mercury, which is the closest planet to, does anybody know how long a year is on Mercury? Yeah. Excellent, 88 days, yeah. So if this is 10 days, that tells you how close this planet is to the star. It's pretty incredible. Okay, I want to talk about one last method, and that's probably the most obvious one, which kind of might be your knee-jerk reaction of how do we find planets. Why don't we just take pictures of them, direct imaging? It's kind of the most naive approach. Why don't we just try to look at these stars? What's the challenge with that? Why is it not so simple? Why can't you just look and try to find the planets? Yeah. Exactly. They're small, and next to these big, bright objects, the star that they orbit. So just by way of analogy, last week was a very significant astronomical event, the total solar eclipse. And this is a video of the solar eclipse from Maine. And I just want to play it. And this was right before the sun became totally covered. And as it gets darker, you might see a little change in the sky. See that dot start to appear? It's going to get a little more prominent. hopefully, on the projector. Want to see that dot over there? Does anyone know what that dot is? It's a planet. This is Venus. This is the planet Venus in our own solar system. And it's always there. It's not like it only appeared during the eclipse, but we can only see it during the eclipse. Why? Because we covered the sunlight. The sun is usually overpowering our ability to see other planets and let alone other stars. But during a solar eclipse, if we can cover the sunlight, then that reveals the other planets that are orbiting it. I actually took my own picture. I got to go to the eclipse last week. I went to Newport, Vermont, and I took a picture, and you can also see Venus right there. So there's the sun. It's actually being blocked here, but just the light just from the corona is already so bright that it just kind of looks like it's a full sun. But that's Venus right over there, which is revealed during the eclipse. And then a professional photographer also took a picture, and you can see all the planets. This is Jupiter, Venus, Saturn, and Mars. Mercury is actually in the same place as the sun. Just happened to be last week, so you couldn't see it. But it was a very well-timed eclipse last week because all of the planets were on the same side of Earth. So you could, if it was clear skies, you could see all the planets during the eclipse. But anyway, this could give us a hint of how we can directly image planets. What would you have to do? Well, you'd have to block out the starlight, and that's exactly what we do. But before we get to that, we're going to have one more physics interlude, which is a question for you. Do planets emit light? Well, the good news is any answer you give is right, because the answer is yes and no. The answer is yes and no. It depends what kind of light we're talking about. So I heard one person say they reflect light, which is very true. When it comes to visible light, which is the sort of light that humans can see, then it reflects light. So you can imagine that you have a star. What do stars do? Stars emit light. They're emitting light in all directions, visible light, among other wavelengths, and some of that gets reflected by the planet. That's why you have a bright side of the planet and a dark side of the planet, daytime and nighttime. And that's how we're able to see Venus and Mars and all those other planets we saw in the visible light, in the type of light that humans see. That's because they're reflecting sunlight. But there's another kind of light that planets actually emit, because planets are warm. So all hot objects emit infrared light. So here's a picture of a dog, and the reason we're seeing the dog is because it's reflecting sunlight, but this is an infrared camera, and you can see the dog is actually glowing. That's due to its own body heat. That's not light that's being reflected from the sun. That's its own light, but it's infrared. It's not visible to the human eye. Infrared, because it's longer wavelength than the red. It's even more stretched out than red, so we call it infrared, and it's not visible to the human eye. Planets are warm, so they emit infrared light. So here's a picture of the outer planets of our solar system in the infrared. They're all glowing in the infrared light. And for those who were at the talk last year on the James Webb Space Telescope, this is the type of light that the James Webb Space Telescope is sensitive to. So let's put that all together. If we want to directly image a planet, then first of all, you want to cover up the starlight. So this is what a star might look like in infrared. You cover it up, and that reveals the planet that's next to it. And we use something called a coronagraph. A coronagraph is a device that you attach to a telescope, which is designed to block out the starlight. And here's a picture that the James Webb Space Telescope took of an extrasolar planet, of an exoplanet. Here's where the star is, except it's being blocked by the coronagraph, so we just have a little symbol there. And this is the same planet being looked at in 4 different filters. And that very first picture, or movie that I showed you, was also taken with the Keck Observatory using a coronagraph. This is also taken in infrared wavelengths. By the way, 20 AU, 1 AU, it's an astronomical unit. That's the distance from Earth to the sun. So these are all like really far from their planet. They're all at least 20 times farther than Earth is from their sun. Think about the selection effects we talked about earlier. You'd imagine that when it comes to direct imaging, this is a selection effect. It's probably going to be really good at finding planets far away from the star and not so good at finding planets close in. Okay, so in summary, we've talked about 3 detection methods. There are others, but these are the 3 we talked about. The transit method, which takes advantage of the fact that the planet blocks starlight. The radial velocity method, which takes advantage of the fact that the planet tugs on the star and therefore causes a redshift and blue shift. And finally, direct imaging, the fact that they actually emit their own infrared light. Okay, now one of the goals of planetary exploration is the search for life, or the possibility of life on other planets. So we need to ask the question, what is it that we're looking for? What kind of planets can support life? Once we know there's a planet there, What do we need? What are the characteristics a planet needs to support life? Any ideas? Yeah. Water, excellent, water. And I should say, by the way, as a caveat, we know life as we know it. We know what life looks like here. So, you can imagine some like really complex chemistry that can reproduce and have all these characteristics that we think characterize life, but aren't quite like the carbon-based life we have on Earth. But the carbon-based life we have on Earth is a pretty good place to start. So, and we know that that requires water. So water is a great, great answer. Yes. Yeah, the striped sweater. A good distance from the sun. Okay, say more. Exactly, like the Goldilocks zone. We call that the habitable zone of a star. You don't want to be too close that it's too hot. You don't want to be too far that it's too cold. And that's related to the fact that we have liquid water here. If it's too close, then it wouldn't be able to be liquid water. If it's too far, then it would freeze. We'll take one more. Again, the green shirt. Carbon. Okay, there are certain compounds that need to be here, including carbon. Exactly. So we can actually get a hint from our own solar system. These are all the planets of the solar system. We know of only one of them that can support life, and you can think about what are the ways in which Earth is unique in that it can support life. And a lot of the ways are ways that you just said, actually. One that wasn't said is that the Earth is rocky. It's a rocky planet. It's not gaseous. It's not a gas giant like Jupiter. Second of all, it's in what we call the habitable zone of the star, meaning it's not too close, not too far. That means it could have liquid water. And by the way, when we say habitable zone, that depends on the star we're talking about. So if you're next to the sun, that will mean around where Earth is. But if you're next to Proxima Centauri, our closest stellar neighbor, which is a much more puny star than the sun, you'd actually need to be much closer in order to be in the habitable zone, because the star itself is not as hot. So habitable zone is a relative term. So you need to calibrate it to whatever star you're looking at. So I just wanted to make that point. It has an atmosphere. Now, by the way, our atmosphere, not only do we have it, but it's a good atmosphere. It's not too thin like the atmosphere of Mars. It's not too thick like the atmosphere of Venus. And what does an atmosphere do? One of the things it does is it regulates our temperature and our climate. And it also protects us from radiation and from solar winds. It's very dangerous to be in space, actually. And one of the reasons that Earth can support life is because we're protected from radiation by both the atmosphere and also by something I didn't write here is magnetic field. And there's some speculation that maybe the fact that we have a moon and the fact that Jupiter is a neighbor of ours might actually be helpful. They kind of are, they enforce order in a sense. And there's some speculation that might be essential to life on Earth. Now, we can learn these things about the planets that we discover. So for example, the transit method and the radial velocity method, from those we can learn about the density of a planet. And from the density we can tell, is it rocky or is it not? And that's how we determine whether the planet we're looking at is a rocky planet or a gaseous planet, by determining the density. We can figure out whether it's in the habitable zone from all the methods, actually. They tell us how far away the planet is from the star. And we can also learn about these atmospheres. We can learn about the atmospheres using telescopes like the James Webb Space Telescope, which detect in the infrared. So I just want to show you an example of really nice data that we have of an atmosphere from a different planet. This is what we call a spectrum, but the point is that you can break up the light that you get when it's transiting, when it's passing in front of the star, and figure out what sort of elements are in the atmosphere. And here they're labeled. You see that there's sodium, there's water, there's carbon monoxide, there's carbon dioxide, sulfur dioxide, all these compounds that we're familiar with are there on this really far away. This is WASP 39b. That's the name of the planet. And it has all these compounds that we're familiar with in its atmosphere. And it's incredible that we're able to probe that from so far away. Some of these are what we call biosignatures, not these actually, but a biosignature is a sign of life. Something you might want to think about is what sort of elements would you look for to not just see that it can support life, but there is life on the planet. If you see oxygen, people think that's a biosignature. The combination of methane and carbon dioxide, that's a biosignature. These are things that are in our own atmosphere. So that's part of the goal of these, of characterizing these atmospheres, is to look for biosignatures. All right. The last thing that I want to talk about is what have we found so far? So first of all, we've found over 5,000 planets, all in the past 15, 20 years or so. And one way you can organize all the planets that we've found is you can organize them by how far away they are from their star. That's what's over here, orbital distance. So over here would be planets that are really close. Over here would be planets that are really far. And by how massive they are. So down here would be really low mass planets, and up here would be really massive planets. So if you would plot all of the planets in our solar system, it would look something like this. So you see that Mercury is really close to the sun and also really low mass. Something like Jupiter is really high mass and farther from the sun, etc. So if you plotted all of the planets that we found, what would it look like? Well, it would look like this. So these are all of the almost all of over the 5,000 planets that we found using these three methods. And first of all, one thing I want you to notice are those selection effects that we talked about. All this green, that's the transit method. And notice they're all so close to their star. Does that mean that all the planets in the whole galaxy are really close to their stars? No, it means that the transit method selects for those planets. Additionally, the imaging method, direct imaging, these yellow dots are all really far away. So you can see the selection effects at play in this graph really beautifully. But this graph also raises some really important questions. First of all, even though we have these selection effects, it's kind of notable that all the planets in our solar system are kind of alone. So is our solar system very unique? That's an open question. We're not sure. Another thing to notice is this area over here. We have a special name for them. They're called hot Jupiters. Called hot Jupiters because they're really massive like Jupiter, but really close to their star. And we're not totally sure how that can happen. Like, we've tried really hard to kind of put physics models together that could show us how a planet can be that massive and also be that close to its star. And that's an open question. So we have a question of hot Jupiters, and is the solar system very unusual? Those are open questions. I also want to focus on just some of the kind of fun, and we'll have time for questions at the end. And I also, I'll say now that I'm going to give Mrs. Amir and Ms. Brandis and everyone else permission to share my email address if you have other questions afterward that we don't get to. So what are some of the fun systems that we found that I just also want to show you? And this is where we could have some of the fun pictures that I told you about, artistic renderings. We found planets around binary stars. So a binary star is when you have two stars that are orbiting each other. And you can actually have a planet that goes around a binary star. And we've found that. This is a paper that Kepler-16 is the name of the planet. And here you see the transits, the little dips. And there's a diagram in this paper that shows you have the two stars and the planet surrounding the two stars. And if you squint really hard, you just might see that it looks like this, something like this, what it might look like. Here's our planet, and it's orbiting two stars. So you'd imagine that this is a planet that would have a double sunset. I don't know if there are any Star Wars fans in the audience. Tatooine, exactly. This is what happens on the planet Tatooine, the double sunset. This was in the 1970s, this movie. And actually don't know when that paper was, but in the past 10 years, we've found that there indeed is a planet that goes around a binary stellar system. Amazing. We've found a planet around Proxima Centauri. I already mentioned this, actually. That's the star that's closest to us, which is pretty exciting because it's our closest stellar neighbor, even though it's still very far away. And it happens to be in the habitable zone, so we are hopeful that we might see other signs that it can support life. This is just the radial velocity data showing the planet around Proxima Centauri. And here's an artistic rendering of what it might look like to be there. And there's the star Proxima Centauri. It's a very puny, it's what we call a red dwarf star. And over here you see this little kind of double star. That's a binary system called Alpha Centauri, which is very close to Proxima Centauri. So this is a very accurate artistic rendering. You would see that even during the daytime, probably. And finally, the TRAPPIST-1 system is something that astrophysicists are very excited about. The reason they're very excited about it is because it's a star with 7 Earth-like planets around it. So hopefully one of them. Well, 2 of them we know are in the habitable zone, E and F. So we're also hopeful that these might have some really interesting planets to look at. All right. I'll skip some of these slides because I want to have time for questions, but just some of the open questions are, how planets form. We're not totally sure. We have a broad idea that it forms out of the leftover material that didn't make it into the star. So we call a protoplanetary disk, and eventually those become the planets, but we're not totally sure how that happens. And that's still an open question that's being actively researched. These are actual pictures of these protoplanetary disks, and you can see these gaps, perhaps where the planets are being formed. Really beautiful pictures of the protoplanetary disk. So we don't know exactly how that happens. And another open question is what we call the dynamics of these systems, meaning how they move under the influence of gravity. Are they stable, meaning how can we determine if 2 planets are going to collide or if a planet's going to get ejected? Can can planets change their distance to the star? That might explain the hot Jupiter's question of how you can have a really massive planet so close to its star. How common are rogue planets? These are all just examples of kind of the open questions that are actively being researched now. I just want to end off with a quote. I don't know if there are any Russian speakers in the audience. But this is a quote that was it's from Yuri Gagarin, who was the first human to go into space in 1961 in this little ball. Crazy. I have no idea who this person is, by the way. It's just from Google Images. But this is him, and he was there, and he was flung around the Earth at 1961. And what did he say? He said, "The sky is black, the Earth is blue. Everything is visible very clearly." Which doesn't seem like such a profound quote until you think about the fact that this was the first person to see what the Earth looks like. Wow, the Earth is blue. We didn't know that until 1961. And my grandfather, something he used to say, he used to love to quote a teacher of his who would say that if you don't know what you don't know, then you'll never know. And I think that this sort of space exploration, not only does it answer a lot of questions that we already have, but it also raises so many more questions that we didn't even know that we didn't know. I think the last 15, 20 years of finding these 5,000 plus planets has answered some questions, but it's raised many, many more and showed us how much there still is to learn and just kind of how rich the universe is with phenomena and information and kind of that we're still yet to understand. And again, this is really a nascent field, and stay tuned in the coming years and decades to see some of what we learn. So in summary, there are planets in the solar system, beyond the solar system. They're very hard to find, and that's why we come up with clever ways to find them. We found over 5,000 so far, and we think there are many, many more. Is there life on other planets? I don't know. We don't know. Maybe. And there are still so many more basic questions we don't know the answer to, and I highly, highly recommend these two websites if you want to learn more. They're awesome. Thank you for your time. We'll have a couple minutes for questions, but I'll also be available afterward.